Well, hello everyone, and welcome to Lecture 5 about the applications of Nash equilibrium. I am David Smerdon. Let's get into it. So far we have seen the theoretical aspects of Nash equilibrium. This lecture now is looking at ways that we can apply what we've learnt to different contexts. And for pure strategy Nash equilibrium, we will look at 3 examples. The first will look vaguely familiar because you will have probably covered it if you've done any undergraduate microeconomics course, and this will be about Cournot competition. We will also discuss bank runs, or the bank run game from finance, which you may have seen in experiments or heard about in the news recently. And from macroeconomics, we will take a look at a famous model, the Cournot model from Diamond. When it comes to mixed strategy Nash equilibria, we will look at an example from a detection game. Okay, so let's start with microeconomics and the Cournot duopoly. We know that in microeconomics, in a competitive market, everyone is a price taker. No single supplier can influence the price. We know about a monopoly as well. In a monopoly market, there is one seller who can influence the price and has no other seller to respond to. So in both of these situations, we cannot really apply game theory. However, quite often in the real world, we find markets that are somehow in between. There's not one producer, there are several producers, but they have enough power that together they can influence the market price. The simplest example is a duopoly, in which there are just 2 agents. One might consider, for example, the case of Virgin and Qantas in Australia, or you can think of, say, the big 4 banks. So we're going to keep things simple, just look at 2. Now there are different ways to analyze a 2-seller market. One is through what's known as Bertrand competition. One is Cournot competition, which is what we'll be looking at and is probably the most common model. And the third is in a sequential game structure where we can look at Stackelberg competition. So sticking with Cournot duopoly then, this is the framework for a duopoly in which the sellers choose quantity that they produce, as opposed to Bertrand competition, which is where they are choosing price. This one, Cournot, is a little bit more realistic, I think, for the real world. So the market price depends to some extent on the sum of the outputs of the 2 firms Q. And that's because we've got a market demand function, P, which depends on the total output Q, and the total output Q is made up of the sum of the quantities chosen by the 2 sellers. Let's make our lives simple if we can. We'll take a market inverse demand function that is linear, such that P of Q is equal to A minus B of Q. Familiar formula for a straight line, I hope. And here we've got it drawn here where the slope is equal to minus b, and we've got our intercept points. Let's assume that each firm faces a constant marginal cost. Now all of these things we are doing, by the way, assuming a straight line demand function, assuming a constant marginal cost, they can be relaxed and the game can be analyzed in the same way with slightly more complicated cost functions or demand functions. But the fundamental analysis doesn't change. So we're just going to keep things simple to see how to analyze things. And it's relatively straightforward then to extend things by making our functions a bit more complicated. So there's a constant marginal cost C, which is the same for both firms, which means that there is a constant average cost of C per unit. And we need to assume that A is greater than C. Remember, A is the vertical intercept up here. It actually won't make any sense if A is less than C because no firm will have any incentive to produce anything. Each firm maximizes its own profit, which we know is total revenue minus total cost. And now we have all the information we need to solve the game. The questions that we need to answer are, what is the level of output by each firm in an equilibrium? And what can we say about the market output level? For example, is it Pareto efficient? Remember, Pareto efficiency talks about whether or not any agent can be made better off without harming any other agent. So it's a very fundamental definition of efficiency. And the second question is, how does it compare to the monopoly or the competitive market output? Now, so far, it doesn't sound much like a game. It sounds a bit more like conventional microeconomics. So let's try to put it in a game framework. What are the three elements that we need for a game? Well, we need the players. We know what they are, firms 1 and firm 2. Oops. We need the actions. Well, both firms in this case, in a Cournot duopoly, are competing on quantity. So each firm chooses its output level, which we will call little q, little q1 or little q2. And we impose some basic restriction that you can't produce a negative output. And we need payoffs. So how do we work out the payoffs? Well, for firms, payoff means profit. Now, given some profile of output, Q1 and Q2, in other words, the strategy profile of the players, the market price is then given by, well, first, P is equal to A minus B capital Q, but we know that capital Q is equal to Q1 plus Q2, so we can just throw that in. And then firm 1's profit, which we call pi, is equal to total revenue minus total cost. Now, total revenue is equal to price times quantity. So this is firm 1's quantity, Q1, and the price, we just throw in the formula that we had above. Minus the total cost, well, we have a constant average cost of C, so it's just equal to C times Q1. Notice importantly that we've written the profit function in terms of Q1 and Q2, which is important because these are the two choice variables that the firms can choose. Similarly for firm 2, as I try to fix up my microphone a bit, firm 2 has exactly the opposite, just symmetrical in terms of changing all the Q2s to Q1s and the Q1s to Q2s. So now we've got all the details to analyze the game. We have the players, we have the actions they can choose, and we have the payoffs given some action profile. Let's try to get these best response curves that we saw in the previous lecture. First question we want to ask is, when will firm 2 produce at all? Well, if the quantity goes beyond A minus C over B, then the price dictated by the market demand will go below C. If the price is below the marginal cost, we know that there is no incentive for the firm to produce. That would violate the marginal benefit equals marginal cost condition for a strictly positive production. Or another way to think about it, each time you produce one more unit, you're actually making a loss on that unit. So it's better to produce nothing. You might remember from microeconomics, we call this the shutdown condition. So if the price goes below C, which means if the quantity goes above A minus C over B, then firm 1 will never produce. So if firm 2 produces more than this amount, whatever firm 1 produces, the price will be below the marginal cost, and firm 1 should do better not to produce. So that's like a very basic condition to get us started. That means we need to concentrate on the case where firm 2 is producing no more than this A minus C over B. And this point is quite straightforward to work out, by the way. We've got the equation for this blue line. We're just looking for the quantity that corresponds to the when the y variable or the price variable is equal to c. So let's work out the profit maximization strategy for each firm. Firm 1 needs to choose C1, so that will be the variable that we use in the derivative in the optimization, taking Q2 as given. So this is our profit function. We want to maximize our profit function, choosing Q1 with the condition that Q1 cannot be negative. So we take a derivative, and then we're going to set that derivative to 0. You may remember this as a first order condition. So we take the derivative of the profit function, pi I. In doing so, we can use the chain rule or the chain formula. So we have these two components that are multiplied together here, the blue and the red, both contain Q1. So first we take the derivative of the red part, that just gives us 1, and we throw in the blue part. And then we do the same on the other side over here. So we take the derivative of this part here with respect to Q1, which is just equal to minus b, and we multiply that by Q1, we set that to 0. And we take away this final part here, which is just c. So that's the derivative, and we want to rearrange that. We end up with this function down here, which is great because it's just got a Q1 and a Q2. That's what we need. If you don't like the chain rule, by the way, there is a very simple way to solve this derivative, which is that you can just write out the whole thing by expanding these brackets so that you have 4 terms, each with Q1 in there, and take this derivative instead. You'll end up with the same thing. Notice that this 2 comes down to join the b in the derivative here. Now, when we rearrange this, I'm going to do a bit more rearranging than the last slide. The first order condition, we want it in terms of Q1, and we throw everything else on the other side. Now, this has found a stationary point, but we don't actually know whether it's a maximization or a minimization point, whether it's a maximum or a minimum. Typically, to work this out for sure, you can either plot the graph, or you can take a second order condition, and to see whether that's greater or less than 0, I'll just do this once. We take the second order condition, we find that it's negative, and that indeed means that our first order condition characterizes a maximum. The simplest way to convince yourself of this is just to plot the initial profit function and see what it looks like. You'll see that it looks like this upside down U, so the top of it is indeed, the flattest point is indeed going to be a maximum. In general, I don't expect you to have to check the second order conditions, particularly when we have standard common profit maximization problems like this. So what this tells us, this condition, the first order condition, is that given each possible Q2 that firm 2 can choose, firm 1's profit maximizing output level is given by Q1. Now that gives us, in other words, firm 1's best response function, the best that firm 1 can do for each possible output of Q2. Now remember, we already decided that if Q2 was greater than this number here, A minus C over B, then firm 1 shouldn't produce at all. So we need to actually break up the best response function into 2 parts. The part of the graph where Q2 is greater than this critical point, and the part of the graph when Q2 is less than that point. And in that case, we can throw in the first order condition, A minus C over 2B minus Q2 over 2. Now we want to work out what the best response function is for firm 2. Now you can go through this whole exercise again, but let's save some time and realize that the two firms are facing symmetrical problems. Because they're facing symmetrical problems, it's logical that when you do your calculations, they'll come out symmetrical as well. So we can actually just immediately write firm 2's best response function as the same thing that we had before, but we're now just changing every Q1 to Q2 and every Q2 to Q1. So now we're ready to solve for Nash equilibrium. A pure strategy Nash equilibrium is a profile of outputs Q1 and Q2 at which every firm is best responding to each other. That means that Q1's choice must be its best response to Q2's, and Q2's choice must be its best response to Q1. So the best response, as we've seen before, is of this form, and similarly for firm 2. But what's a bit tricky for us to solve initially is that we don't really know which of these two parts of the best response function we're dealing with, and it would make our lives so much easier if we could narrow that down to one. So what we're going to do is we're going to prove that no firm can ever produce 0 in a pure strategy Nash equilibrium. We'll do that by way of contradiction. So by way of contradiction means we first take the opposite. So we assume that there is such a Nash equilibrium in which firm 2's best response is 0. And then we want to show that it cannot be 0. So if it is 0, then we know that means that Q2 is definitely less than A minus C over B. Remember, A is greater than C. So then we know that Q1 should produce this amount here, but Q2 is 0, so we can get rid of that. So Q1 is producing A minus C over 2B. But if Q1 is A minus C over 2B, that is definitely less than A minus C over B. So now if we look at firm 2's best response, I'll go back and show you. So if we go to firm 2's best response, we know that firm 1 is now definitely producing less than A minus C over B, which means that firm 2 must be producing a strictly positive amount. So the best response of firm 2 in this case requires that Q2 star is greater than 0, but our initial assumption was that Q2 is less than 0. And hence, by using this proof by contradiction, we have shown that if a Nash equilibrium exists, then it must be that Q1 and Q2 are both strictly positive. And we know that there must be at least one Nash equilibrium in the game. Another way to think about this is, if one of the firms is producing 0, then at least one of the firms must have a profitable deviation. Either it's a situation where say firm 1 is producing 0. Either firm 2 is producing such that firm 1 has no incentive to produce anything at all, but in that case firm 2 could do better by changing its output. Or firm 2 is maximizing its profit, but if it's maximizing its profit, then firm 1 could do better by entering the market. So in other words, you can never have a situation where both of them are happy. In that case, we can make our lives again a bit easier because we can rule out that second part of the best response function and just focus on the top part of the best response function. So Q1 star must then be equal to this strictly positive amount and Q2 equal to the symmetrical one. And then our lives become straightforward because we've got these two unknowns and we've got two equations. And you can use whatever method you want in order to solve these two linear equations in two unknowns. And if you do so, no surprise, you get symmetric conditions. Q1 star is equal to A minus C over 3B, and Q2 star is equal to A minus C over 3B as well. Let's see how this market output now and this market price compares to other market structures that we are more familiar with, but which don't involve this element of game theory. In a monopoly, we find the marginal revenue curve. We set that equal to the marginal cost, and that will track up to the demand curve to give our price and our quantity. In perfect competition, the marginal cost is equal to the price, In that case, we end up with QC here and a price equal to the marginal cost, as I mentioned over here. In a Cournot duopoly, I guess it's reasonably logical. It's a little bit like perfect competition, but a little bit like monopoly. We end up in the middle for both market output and for market price. Actually, an interesting question that you might want to already think about is, what happens if one of these two firms could actually choose its quantity first and commit to sticking to it? Would that change things? Would there be an advantage to going first? Would there be an advantage to going second? Would it be the same as one of these three market structures? Okay, we won't look at that right now. What we'll do instead is turn to another familiar type of microeconomic market structure, and that is monopolistic competition. With monopolistic competition, there can be many firms in the market, but the products are no longer homogeneous. They are usually differentiated in some way to do with brand or some other feature, which means that there is some market power for each firm. So a simple example, Coca-Cola and Pepsi. They have two very similar products, but also different in the sense that there are people out there who will only buy Coca-Cola or who will only buy Pepsi, for example. So they have, each of them has some power. They are not perfect substitutes. And there are many other examples of products that need to be aware of what's happening in other product markets. This usually happens when there is interlinked demand. So we'll do an example. We'll stick to our sugary drinks. We'll call Pepsi Firm 1 and Coke Firm 2. First question, of course, are they substitutes or complements? And the real part of that is, should we be putting a plus or a minus in here? Have a think about it, pause the video if you need. Well, these are substitutes for each other, and as such, when the price of Coke goes up, more people are going to want to switch to Pepsi. So there should be a positive relationship between the price of Coke and the quantity demanded of Pepsi, and that gives us a plus sign. We'll assume that things are symmetrical in that we've got a similar demand function for Coke, and they are again interlinked. So notice the key difference here is that we've got the other firm's price of their product appearing in the given firm's demand function. Okay, we'll assume that both firms again have constant marginal costs. We'll just complicate things slightly by allowing for those two costs to be different, C1 and C2. But again, just like in the previous example, we can make all of these features more complicated, these functions more complicated, and besides making the math a little bit more complicated, nothing really changes in the way we approach the analysis. So, what I want you to do is actually to try this at home. So I'm going to give you 4 questions to answer, and I want you to pause the video once we've gone through describing the questions, have a go at them, and then we'll go through some work solutions. It may take you some time. So, question 1, what are the price functions? These are written in terms of P1 and P2, and the parameters will be Q1 and Q2. So on the right hand side, we'll see Q1s and Q2s as well as the fixed variables. Question 2, what is the condition under which each firm produces anything? Just like in the previous example, we found the threshold for Q2 above which firm 1 would produce nothing, and below which firm 1 would produce something positive. So we want to find that again. Firm 1 produces a strictly positive quantity so long as Q2 is less than what? You want to be able to fill in these blanks. Question 3, what are the profit functions? got them here in terms of pi again. So pi for firm 1 is the profit of firm 1. It will be in terms of Q1 and Q2. We want everything in terms of Q1 and Q2 rather than P1 and P2 because, again, we're assuming that firms can only choose the Qs. The Ps come out of that, but the P also depends on the other firm's Q. But firm 1 has the power to choose Q1. At least firm 1 has that power, and firm 2 has the power to choose Q2. So those are the choice variables. We need those in the profit function. Question 4, what are the first order conditions for profit maximization? We get that by setting the derivatives of the profit functions equal to 0. And I lied, it's not just 4 questions, there's a 5th question as well. I guess the most important one, what are the 2 best response functions? These will again be made up of 2 parts, but you only really need to fill up the first part. But both parts of the first part are important. So the best response function for firm 1 is what firm 1 should produce given firm 2's production. And there will be 2 amounts here. There will be this 0 amount which comes from what you would have found before, what is the condition under which each firm produces anything. And the top part, that will be coming from your first order condition, so your answer to question 4. Okay, 5 questions. I'll leave that with you. Pause your video now, and then we'll go through the solutions. Okay, let's go through the answers. The first question was to find the price functions, that is P1 in terms of Q1 and Q2. So what we can do is we can rearrange this equation here to get P1 on the left-hand side. We'll get P1 is equal to 100 minus Q1 plus a half P2. That doesn't quite help us because we want this P2 to disappear and be in terms of Q2. So we'll get 100 minus Q1 plus a half, and then instead of this P2, we'll rearrange this thing here instead. We'll rearrange that. Remember, the P2 over here means 100 minus Q2 plus a half P1. So when we do that, we get something slightly messy. We get this. Q1 is equal to 100 minus P1 plus a half 100 plus a half P1 minus Q2. So at least we've got rid of the P2. And now we've only got P1, Q1, and Q2, which is good. That's what we want. We need to get this P1 onto the left-hand side. First, we'll do a little bit of rearranging here to collect these P1 terms. Just expand out these brackets and then put these P1s together to get 3 over 4 P1 here and everything else on the right. Now we want to take this guy and isolate it on the left-hand side. So we'll throw that over there, throw the Q1 from here over to here on the right-hand side. And the final step, take this 3/4 and divide everything on this side by 3/4, or in other words, multiply it by 4 over 3. Do a little bit of simplification and we get something that is not quite as messy as what we had before. P1 is equal to 200 minus 2/3 Q2 minus 4/3 Q1. So what are the price functions? The answers are symmetrical, again, just changing the Q1s to Q2s and vice versa. How did you go? Did you get it? What is the condition under which the firm produces anything? Well, to make a positive profit, it must be the case that P1 is greater than C1. Because we have a constant marginal cost, that means we've got a constant average cost. It must be the case that the price of an item is more than the cost to produce that item. Well, we know now what the price of the item is. So we're looking at a case for firm 1. When should firm 1 produce at all? Imagine that firm 1's not producing and it's deciding whether to produce at all. So in this case, we've only got Q2 in the market. So the price is 200 minus 2/3 Q2 in this case. Sorry, I should be looking up here. the price that firm 1 faces is 200 minus 2/3 Q2. At the moment, firm 1's not producing anything, so we've got that here. And that price must be greater than firm 1's marginal cost C1. And if that's the case, then firm 1 will produce. If not, firm 1 won't produce. So we've got this equation, but we really want this in terms of Q2. We want everything in terms of Q2 because when we write the best response function for firm 1, it will depend on what firm 2 produces. So we just want to rearrange that as follows. To make a positive profit, to produce anything, firm 1 requires that Q2 is less than 300 minus 3/2 C1. And again, we're going to have the symmetrical equivalent for firm 2. Firm 2 produces so long as Q1 is less than 300 minus 3/2 C2. All right, we're making some progress now. What are the profit functions? Well, profit is going to be equal to price minus marginal cost, all multiplied by Q1. Or in other words, it's going to be equal to total revenue minus total cost, where total revenue is equal to the price times Q1, and total cost is equal to the marginal cost times Q1, C1 times Q1. So we can put that all together because we know the price now. We've got the price, we've got the marginal cost, which is constant, so it's also the average total cost. So this is essentially equal to the price minus the average total cost. Oops, well, okay, you got the idea. And we can do the same for firm 2, profit of firm 2. And what's nice about this, well, the C1s and the C2s, those guys are fixed. Everything else in here, we've only got those Q1s and Q2s. And that's really important because if we're competing on quantity in Cournot, we're only choosing quantity, which means that when we take a derivative, it has to be with respect to those choice variables, Q1 and Q2. So when we work out the first order conditions, we want to be able to take a derivative, not with any p's in here, because the p's depend on q's, but of just Q1 and Q2 and fixed variables. So we do this, we take a derivative, do it any way you want. We end up with this first order condition for firm 1 and this first order condition for firm 2. Now to get the best response functions, we need to rearrange those. So firm 1's best response function, we're just going to rearrange it, putting Q1 on the left. So we just take what we had before, the first order condition, put Q1 on the left. We end up with this as a best response function if firm 1 is producing at all. So if 300 minus 3/2 C1 minus Q2 is greater than 0. And that if statement, that condition here, that threshold, is something we just worked out from question 2, when we worked out when will firm 1 produce at all. So if this condition doesn't hold, if Q2 is less than or equal to 300 over 3/2 C1, then firm 1 produces 0, so we just write 0 otherwise. That's good enough. We do the same for firm 2. We get again the symmetrical condition, just changing the Q1s to Q2s and vice versa, and the C1 to C2. And we have our two best response functions. And that's great. Now we have everything we need to solve the game. In fact, it's essentially solved. But if we want to work out equilibrium, now we just need a few little extra pieces. So let's see an example now where we set the marginal costs equal. We'll set them both at 40. And we can see the equilibrium that comes out by plotting these two best response functions and finding their equilibrium or their intersection point. So if we plot these two functions, you can see that we've got, again, something that looks pretty symmetric coming out here. Because the price for firm 1 is greater than C1, and the price for firm 2 is greater than C2, firms are making positive economic profits. And the intersection is at exactly 48. So the price for firm 1 and the price for firm 2 is 104. These positive economic profits, as I mentioned, means that that's a reflection of the fact that it's not a perfectly competitive market, but each firm has some market power, which means that it's not quite a monopoly, but they're still getting those economic profits. Okay, so that was the first application. All right, let's move on to a macroeconomics example. Now, you might remember from early days in economics, Adam Smith in the 1700s, perhaps the godfather of modern economics, talked about the degree of specialization that people come up with. We know that specialization is important to get the advantages of comparative advantage. However, it's limited by the extent of the market. And in modern macroeconomics, this is related to the poverty trap. The poverty trap has been used to explain why developing countries have struggled to catch up to developed countries, even though in theory they should be catching up quite quickly, given that they have access to production technology now from developed countries that took the developed countries a long time to develop. So why are they still stuck in this slower growth than we would have expected or have hoped? It's also related to the business cycles that we experience even in developed economies. We can have situations where unemployment starts to rise because production is falling, which means that wages go down. When wages go down, consumers spend less. But when consumers spend less, then producers have less incentive to produce because demand is decreased. So production seems to pull back a bit, but that leads to further decrease in wages of consumers and so forth. So we can end up in these sort of parts of the business cycle. We would like to get an idea of how these things can exist in light of a strategic interaction in a toy economy. So we're going to look at an island. Assume there's a tropical island in which there are lots of coconut trees. Coconut is the only consumption good on this island. All coconut trees are of the same height. We'll call them 1 in whatever the local unit of measure is. But they bear their ripe coconuts at different heights along the tree trunk. Now, each morning, the island chief runs a lottery where he randomly assigns islanders to a coconut tree for that day. So when you wake up in the morning, you check your email on the island and you read, okay, today tree number 17 is my coconut tree. You go out and find it, and then your decision is, should I climb the tree or not? You see where the coconut is and you make a decision. Should I climb it or not? Now, it takes more effort to climb high than it does low, of course. And if one climbs, one gets a coconut. Otherwise, you go hungry for the day. The question is, do you climb or do you not? Now, in the afternoon, it turns out that you cannot eat your own coconut. This is a cultural norm. So you must find a partner with which to exchange your coconuts in order to eat a coconut. If you find someone and you trade, you eat it. If you fail to find a partner, you go hungry for the day and your coconut is wasted. Again, what's going to happen? Do you climb the tree or not? Well, why is this a strategic game? Well, if few people go around with a coconut in the afternoon, then it's much more difficult to trade and find a partner. It's more likely you'll go hungry, so it's just not worth climbing in the morning. But if everyone thinks that way and nobody's climbing in the morning, then there will be few people going around with a coconut in the afternoon with which to trade. So again, we're falling into this sort of cycle. In other words, the optimal height for you to climb depends on how high the other islanders are climbing. And whenever you've got a situation where your best decision depends on the decisions of others, you have strategic interactions. Okay, so why is this island interesting? Well, we need to decide how much effort in general to put into market production if we're a producer in an economy. But for most economies, people who produce stuff, whether you're making coffee, making t-shirts, making carrots, whatever, you're not surviving just on consuming your own purchases. We don't live in this sort of subsistence economy anymore. So your happiness, your welfare depends to quite a large extent on your ability to exchange your goods and services for others. And if you don't have that ability, or that ability is hampered, you have less incentives to put into your production. But if everybody has that situation and they're putting less effort into production for that reason, then it becomes harder and harder to exchange any output for goods and services in the market. And this leads to these recessionary sort of periods. But we're looking at that in a simplified format, also kind of a fun format. So let's formulate this island now as a game. Players, actions, and payoffs. That's what we need. The players are the islanders. Now, we don't need to know how many there are, but just to specify that the number is large, and that way we can work in proportions. The actions, well, it's just the maximum height that the islander is willing to climb, and that's denoted by H, which obviously has to be somewhere between the base of the tree to the top of the tree. And the payoffs are equal to the gross payoffs minus the cost of effort. We say that you get a payoff of 1 if you eat the coconut, 0 if you go hungry. The cost of effort, we'll call that a function C of H, where H is the height that you climb. We'll call that function strictly increasing, as in it requires more effort to climb higher, and we'll make it weakly convex in the sense that it's getting more and more difficult to climb up the tree. Easy to climb up a 30 centimeter tree, much harder to make that extra 30 centimeters between 5 meters and 5 meters and 30 centimeters. And of course, there's no effort if you don't climb. Let's talk about the production technology. The height of the coconut on the tree for each individual is a random variable. So given a particular height H, the probability that the coconut is below H is denoted as f of H equals the probability that the coconut is below of H. This capital F of H you might have seen before, that's actually a cumulative distribution function for the random variable. So if all islanders decide to climb no higher than H, then a fraction of them, f of H, will have a coconut in the afternoon. So you climb up to the height that's there, and for those who find a coconut somewhere on their path to where they climb to, they've got the coconut. For the rest, where the coconut is higher than that H, they're not going to get a coconut. So the fraction who are actually getting a coconut then is this cumulative distribution function, which reflects the probability that their coconut was below that H. Let's talk about the matching technology now, which happens in the afternoon when there's trade and exchange. So let E be the fraction of islanders with a coconut in the afternoon. Then the probability that an islander with a coconut finds a partner to trade with, we'll call that probability B of E. Now, what do we need to know about this probability function, B of E? Well, it must be increasing in E. That is, the more people around with a coconut, the higher the chance that you find someone to trade with. If there are no people to trade with, then you're not going to find anyone for sure. So that probability will be 0. We've made things look quite complicated. We've thrown in a lot of different functions. We've kept the functions reasonably general as opposed to previous examples where, for example, we had a fixed marginal cost. Now we have an increasing effort function, we have different probability functions, we have a cumulative distribution function, and because we're dealing with probabilities, things seem complicated. To make things simpler, we'll start with a choice rule. The choice rule is as follows. How does a rational islander choose whether or not to climb her tree? She comes to the tree, and in the morning she says, I will climb my tree if the coconut is no higher than the height h on my tree, where h upper bar is the threshold for the islander. It's the height at which she rationally decides it's no longer worth putting in effort to climb anymore. And at this point, she changes her action from climbing the tree to not climbing the tree. So if the coconut is higher than that threshold, I'm not interested. If it's lower, I'm going to climb. And if you think about it, that makes sense. People use these thresholds all the time. They might not explicitly use them in their mind, but if somebody's swiping on Tinder, they're swiping left, they're swiping right. There is some threshold when they look at the pictures whereby they change from swiping left to swiping right. Now, they may not explicitly have that in their minds, but it must exist. There must be some sort of threshold. So here we're just making it explicit that there is a height threshold on the tree. Now, how do we find equilibrium in such a complicated game? Well, we're going to particularly focus on finding a symmetric Nash equilibrium. Good artwork there. So that is that everyone chooses that same action in equilibrium, which makes some sort of sense. We've found symmetric equilibria before when looking at the Cournot Duopoly game in terms of Q1 and Q2. Quite often they were the same. And here we haven't said anything that really makes these islanders different. I mean, these islanders are more or less the same people, just that they're going to be randomly given different circumstances when the lottery is revealed. So we're interested in finding this maximum height that each islander will choose. And the equilibrium we're looking at can be completely described then by some threshold height or cutoff height, which we'll call H star. So this H star is a point where everybody will climb if their coconut is below H star, and if it's above H star, they won't climb. So this is going to be a threshold that we're looking at that is identical for everyone, and that's why we call this a symmetric Nash equilibrium. It must have the property, this H star, that just like an equilibrium is like a poster on the wall with recipe for everyone on how to act, and if you see that poster, you believe that everybody else is following that recipe. So this H star should have the property that if everybody is climbing to H star, and no more than that, so you know that everybody is following this rule, then you must also be willing to climb to H star and no more. So you will follow your rule if you believe everybody else will follow theirs. Now, why do islanders care about the height that others are climbing to? Well, they don't really care for some altruistic reasons. They care because it determines the probability of those islanders getting coconuts, which determines the probability that you will be able to exchange your coconut in the afternoon and thus not go hungry. That's what you care about. So let's put it in those terms. If everybody else climbs to H star, then how many will have a coconut? Well, if we were to guess, it will be exactly the probability that the coconut is below that height H star, which we know what that is. That's the cumulative distribution function, capital F of H star. So that's the proportion of the population we expect will have a coconut in the afternoon. And if it's a large enough population, we can be almost certain that that's indeed the proportion that will have a coconut. So if this number that comes out of this function f of H star, if that number of people, or that it's actually a proportion, if that proportion of people has a coconut, what's the probability that you meet somebody with which to trade your coconut? Well, remember that this probability was given by B as a function of E, where E was the proportion of the population with a coconut. Well, we know what that proportion is. So instead of E, we can put in this f of h star. And if I'm very good at art, I can write here to say that this was E, but now it's f of h star. So we're getting closer. What step are we missing? We're missing expected payoff. So if everyone else is climbing to h star, I want to know what my expected payoff is from climbing, my expected payoff from not climbing. And if my expected payoff from climbing is higher, then I'm going to climb. So at the moment, I'm not saying anything about me climbing to a height of h star. I'm just going to work out what my best response function is if everybody else is climbing to h star. And it can be any h. Let's work out what my h is. Well, if I climb to height h, I get this probability of finding a partner in the afternoon plus the probability that I don't find a partner in the afternoon. And that means I get 0 here. Whereas if I do climb, I get 1. Minus the cost of my effort that I put in. And that's, remember, C, which is a weakly convex function in terms of the height that I climb. If I don't climb, I'm going to get a 0. So I can rearrange that a little bit as follows. And now things are starting to simplify a little bit. I've got a payoff that I get when I climb a height of h to get a coconut, expected payoff, and a payoff that I get if I don't climb, which is just equal to 0. So when is it worthwhile for me to climb this height of h to get a coconut? Well, it's worthwhile only if climbing this expected payoff here is better than the alternative. In other words, my expected payoff from climbing must be greater or equal to 0. And I can rearrange that as such. That means that if h star is the height that the others are climbing, the maximum height h that I'm willing to climb must solve this function where we've got this maximum h in here. Because if I climb any higher than this point, then this inequality here will reverse. Because remember, this C of h is increasing in h, nothing is changing on this side. So this is the maximum that I'm willing to climb. Any more than that, and I wish that I hadn't have climbed. So h upper bar is my threshold height. So just to repeat that, if h star is the height that all others are climbing, what's the maximum height that I am willing to climb? It must solve this equation. Okay, so I've worked out the best response for an individual, given that everybody else is playing h star. If I want a symmetric equilibrium, it must be the case that there is some joint threshold height. H upper bar is what we call a threshold, and that needs to also be h star, such that if others are climbing up to h star, I would like to climb up to h star. So we want to sort of equate these things now, so that in that situation, nobody would have an incentive to deviate from their strategy. In other words, we simply need to replace this h bar here with h star here. And that's nice because we now have our symmetric equilibrium condition. Or in other words, we have the equation that characterizes a symmetric equilibrium. So that's our equilibrium condition. Now let's try to work out a few features of this. We've made this condition very general because we have these generic functions c of h, b of e, and f of h, which we've put some basic conditions on, that b of 0 is 0, that f of 0 is 0, that c of 0 is 0, those sort of things, and that c of h is weakly convex. But let's get some more insight by looking at a few examples. The first thing to note, we said that c of 0 is 0, and we said that b of 0 is 0. and f of 0 is 0. So if we put 0 in for h star, we'll get 0 on both sides. In other words, h star equals 0 is always a solution. Now, let's throw in one example of a b, this sort of concave function here, b of f of h, and put in some weakly convex c of h. What we can see is that they intersect here at 0, but that there can also be a second equilibrium. In this case, there is a second one at some other h star. So let's look at some specific examples. We've solved for the generic equilibrium condition. Now let's suppose that we have these rather uniform type of functions for the probabilities and a convex, strictly convex quadratic function for the cost. So b of e is equal to e, f of h is equal to h, and we'll call c of h equal to 2h squared. So then what do we get when we plug that into our equilibrium condition? Well, we get b of h star instead of b of f of h star because they're equal to each other. But b of e is e, so b of h star must also be h star. So we end up with h star is equal to 2h star squared. And we can plot this, and we can find exactly that h star that solves the condition. Of course, we still have 0, but we also have another one now of a half. So there are two equilibria. Let's make it a bit more complicated. Let's add a linear cost function, but make the cumulative probability function a lot more complicated. When we throw this in now, we get this big ugly thing here for the f of h star. We can write that in terms of b of f of h star, and on the right we can throw in c of h equals h, so this linear cost. Rearrange this function, and now we see that we actually get three solutions. We get 0 as before, we get a half as before, and we also get 1 as before. And this is important because actually in the real world we often find situations like this where we have multiple equilibria, and quite often in more dynamic models we find, well, we can talk more about the stability of equilibria. Now, we will discuss this to some extent in the final module of this course when we look at evolutionary game theory. But there are other ways to look at stability in dynamic settings. And what we often find in the real world is that the maximum equilibrium, here h is equal to 1, and the minimum equilibrium, h is equal to 0, are stable. Whereas this intermediate equilibrium here, h star, is actually unstable in the sense that you shouldn't think it as something that's likely to occur, but more that it represents a tipping point. That is, if everyone is choosing some threshold h that is less than a half, they're climbing to a third or something, then over time they will notice that there are profitable deviations and they will move towards 0. They will move in a predictable direction. Whereas if everyone was, say, choosing 3/4 or something a little bit more than a half, they would then look around, they would see, I can do better if I change my behavior. But again, it would be in a predictable direction. They wouldn't move down to 0, they would move up to 1. So this half, this unstable equilibrium, kind of refers to a tipping point in common parlance, or some sort of threshold. And this is a threshold that we often see in models about poverty traps. So if you're in a situation before you get to that threshold, in that you don't have enough development in your market economy, you don't have enough production, you don't have enough exchange of goods and trade, it's likely that you will be stuck in that bad equilibrium. So a poverty trap then is an inefficient Nash equilibrium that can be quite hard to get out of. It also shows why countries with similar fundamentals can find themselves in very different levels of development because of accidental shocks to the system might move them above or below that tipping point, which means that in the long run they end up at completely different points on the economic development scale. And there's more discussion about this in a well-known paper in the Journal of Political Economy that might be interesting to look at. We'll now look at an example from finance, but only briefly, because this was going to be the experiment which we weren't able to run for obvious reasons, but will be discussed in part of the tutorial and the tutorial consults. You can also find that tutorial explanation as a Zoom recording. So this experiment was related to the bank run games, which is very much topical at the moment given what we've seen in the supermarkets with different sorts of goods. Now, many of you will know that banks don't actually hold all of the reserves of money that people have deposited there. So you and I will have bank accounts, but actually if we add up all the money that the banks have stored, it would definitely not cover what's written in our accounts in terms of the money we've got in there. Now that's fine, that's a fractional reserve banking system, which makes sense when you've got strong financial institutions. However, if everybody went to withdraw their money at the same time, just like if everybody went to buy toilet paper at the same time, we would have a problem. There wouldn't be enough supply to go around. And in bank situations, that's quite important because there's not enough money. People run to the ATMs, a situation that we've seen, for example, in Greece a few years ago during the European financial crisis. So in a good banking equilibrium, which is where we normally find ourselves, depositors only withdraw their money when they've got a liquidity need. We're totally fine with most of our money only virtually appearing as numbers in our online bank account. That's okay, we don't need it all the time. So everything's fine. But there is a Nash equilibrium, just like we've seen with toilet paper and with other items, where regardless of what you need right now, everyone withdraws money. And nobody wants to deviate from this. Nobody wants to take a step back and not withdraw money, because if you believe that everybody else is withdrawing, then not withdrawing means you lose your deposit. So by withdrawing, there is at least a positive probability of getting something back, and that makes it a profitable deviation. So actually, with some of these crazy examples in the supermarkets that we've seen, there is a rational explanation for why this is going on. We've just moved ourselves from a good equilibrium to a bad equilibrium because of some shock to the system, some false belief about supply shortage, or whatever it could be that triggers this process. But the movement, once we're out of a good equilibrium and past a certain threshold, the movement then towards a bad equilibrium, the stockpiling and hoarding of supermarket supplies, is rational behavior, because it is actually the maximizing behavior for each individual, and nobody deviates from this. Okay, so deposit insurance can reduce this incentive for withdrawals, particularly when the government guarantees the money you've got in the bank or taxes those who withdraw early. What happens in experiments when we run this? Well, we didn't manage to run it this year, again, for obvious reasons, but we can see that different tutorials groups in the past ended up in very different sorts of equilibria. This is a particular tutorial group where even across time, the percentage of withdrawals, the percentage of group members who took their money out didn't change too much, even when we changed the bankruptcy return, different forms of insurance, those sort of things. But then there were other tutorial groups which very quickly found themselves in a bad equilibrium, these sort of liquidity traps where we had almost complete withdrawal rates from members of that tutorial. There are some theoretical models about this, again, some work by Diamond that you can look up. Okay, one more example for today, and now we're going to look at mixed strategy Nash equilibria. So this example comes from the world of professional sports and drug testing, doping. So a commentator argues there are more drug tests these days, but the detection rate of the test remains unchanged. This means the drug test is ineffective in deterring athletes from doping. This seems like a pretty logical statement to say if the number of drug tests are higher. Let's see whether or not we can get some evidence from our theoretical models. So, drug testing is an application of the matching pennies game. Player 1 is an athlete who's choosing whether or not to use drugs or steroids. Player 2 is the official who decides whether to conduct a drug test on player 1. And here are the payoffs. So let's try to find Nash equilibrium of this game. Remember, player 1, if doping and gets checked, that's a bad outcome. If doping and doesn't get checked, that's a good outcome. Good for them, I guess. And staying clean is somewhere in the middle, just a neutral payoff. What about for the official? Well, the official wants to check, particularly if he or she suspects the athlete of doping. But checking is costly. It wastes time and resources. If the athlete's clean, you'd prefer not to have checked. However, you don't want to not check if it turns out that the athlete was doping. So again, we've got this matching pennies sort of situation, whereby if we try to find the pure strategy Nash equilibrium, there's always an incentive for someone to deviate, and we just sort of move around in a loop. But we know from Nash that there must be at least one Nash equilibrium of any normal form finite game. So then it must be a mixed strategy equilibrium. So we'll solve this in the way that we've seen in the previous week. Let P be player 1's probability of doping, and let Q be player 2's probability of checking. Now for player 1 to be indifferent, it depends on player 2's probability of mixing. So the Q for player 2 must solve, it must be the case that player 1 is getting the same payoff from doping as from being clean. So the payoff from doping is equal to -1 times Q plus 1 times 1 minus Q. -1 times Q plus 1 minus Q. The payoff from being clean is 0 in every case. So these two things must be equal. So for player 1 to be indifferent, player 2 must be mixing with Q equals to a half, or just mixing in equal probabilities. For player 2 to be indifferent, it must be the case that player 2 is getting the same payoff given the mixing strategy of player 1. So for player 2, it must be the case that the payoff from checking, which is 1 times P plus -1 times 1 minus P, is equal to, that's this part here, 1 times P minus 1 times 1 minus P, has got to be equal to -1 times P plus 0. So that's this minus P here. We solve for P, we get P is equal to a third. So very quickly, we can solve the mixed strategy Nash equilibrium of this game. It must be P is equal to a third, so a third, 2/3 are the mixing proportions for player 1, and a half for player 2. Okay, that's nice. We found the equilibrium. The question is, what is the probability that a drug test would turn out to be positive? Because that is conditional on actual checks being conducted. What's the probability that the athlete is caught? Well, that's just going to be equal to P, the probability that they are doping, because we've got this equilibrium condition from before for player 2. So the drug test has a detection rate equal to a third. Excuse me. Now what happens if the payoff from doping increases from 1 to some number alpha which is greater than 1? In other words, we say that the payoffs have gone up, maybe there's more sponsorship, more prize money, something like this. Let's see how the Nash equilibrium changes. Well, again, the fundamental game structure is the same. It's still matching pennies. There's still going to be no pure strategy Nash equilibrium. For player 1 to be indifferent, it's got to be the case that, again, the payoffs for player 2 are equated. So it's got to be that Q must solve, it's got to be the payoffs of player 1 need to be equated, given the mixing strategy of player 2. Apologies. So that must be that Q must solve. It must be that -1 times Q plus alpha times 1 minus Q, that's this part here, is equal to the payoff of being clean, which is just equal to 0. So we get a new probability, a new mixing strategy proportion for player 2 in terms of Q, for player 1 to be indifferent. For player 2 to be indifferent, well, remember player 1's randomization probabilities are determined by player 2's payoffs, but we haven't changed player 2's payoffs here. So those player 1's randomization probabilities, those P's, won't change for that reason. And this is the key concept of mixed strategy equilibrium that takes a while to get your head around, that a player's mixing strategy, mixing proportions, really is determined by the other player's payoffs. Because once you see what the other player is doing in equilibrium, it actually doesn't matter what you do anymore. Remember the example of choosing the weighting of your marks, all tutorial participation or all final exam or some mix of the two. Well, if you got 90% in both of these, it doesn't matter which category you choose actually. So it's the same thing here. That proportion that you choose in equilibrium is determined by the other player's payoffs. So we end up with a new Nash equilibrium where player 1's strategy profile doesn't change, but player 2's, the officials, does change. The question is, are drug tests more frequent or less frequent than before? Well, before we had a case where this was equal to a half. Now it's equal to alpha over 1 plus alpha. But alpha is greater than 1. In that case, alpha over 1 plus alpha is definitely greater than a half. So in that case, drug tests are more frequent than before. Now what's the new detection rate? Well, remember the detection rate was P. But P, player 1's proportion, mixing proportion, is determined by player 2's payoffs, which haven't changed. So that's the same as before. So when the commentator makes this argument, there are more drug tests these days, but the detection rate of the test remains unchanged. It's nothing to do with the effectiveness of the drug test. So what are we comparing? Well, here we've got player 2's randomizations. They're the ones that have changed from the old payoff matrix to the new payoff matrix. And we've got the payoffs to player 1 written down below. So remember that in the old payoff matrix, Q is equal to a half, and in the new payoff matrix, Q is equal to alpha over 1 plus alpha. But now we can see what happens if the official keeps the same mixing strategy even though the payoffs have changed, or alternatively uses a new proportion strategy in the old payoff matrix. So in the new payoff matrix, if Q remains at a half, that is the official doesn't change their behavior from the previous equilibrium, what will the athlete do? Well, in this case, the athlete will always dope. So in the new payoff matrix, if Q is equal to a half, then this number here, -1 plus alpha over 2, is strictly positive, strictly greater than 0. So player 1 will always dope. In the old payoff matrix, if the Q is at the new level, so if the official is using this new mixing probability, then the athlete will always stay clean. But if the athlete always stays clean, then there's an incentive for the official to not check as much. Finally, taking us all the way back to the very first 5 minutes of the very first lecture, that very first clip of Batman the Dark Knight, where the Joker and his cronies, his gang members, rob a bank, but only the Joker comes out unscathed with the full loot. You might be wondering what that's got to do with this course. Have you got it? No? Well, here is a game to think about at home that might add some context. I want you to think about this, try to solve it, and we'll discuss it next time. It's the pirate game. There are 3 pirates, you, Captain Barbossa, and Jack Sparrow. And you arrive from a lucrative voyage with 100 pieces of gold, and you're going to split up the money according to the pirate code. The pirate code depends on the hierarchy of leadership. So you are the most senior, then there's Captain Barbossa, and then there's Jack Sparrow down the bottom. And there's a voting process that all pirates have to follow. It's a series of proposals, but with a deadly, lethal twist. You're the strongest pirate. You offer a split of the gold. There are 100 pieces, so you could say, for example, nothing to me, 10 to Barbossa, and 90 to Jack. It would be a strange offer, but you could do that. Then all of the pirates, including the proposer, vote on whether or not to accept the split. The proposer holds the casting vote in the case of a tie. You can't have a tie with 3 people, but you can with 2. Now, why does it matter? Well, if the pirates agree to the split, then you take the gold and you go your separate ways. But if the pirates don't agree, they gang up on the proposer, which would be you for the first proposal, and throw you overboard, where they perish, and then the next pirate takes over the offer and offers a new split of the money. And we follow that process until a proposal is accepted. So what do pirates care about? We've got the players, we've got the actions, we need the payoffs. Well, obviously there's gold, but pirates also like to live. In fact, pirates care first and foremost about living, not getting thrown overboard. Conditional on living, they care about getting as much gold as possible. So the question is, you're the first, it's your turn as the first highest member of the leadership team of the pirates to make your proposal. What should you do in order to get rich and not die trying? In other words, how can you stay alive and maximize your gold? Have a think about this. It's a fun problem, but it's an interesting problem, I think, and we'll discuss the solution next time. See you later.